Welcome back to Math for Technology. We are finishing up Chapter 5 with the applications of the trigonometry section. In this section we're going to use several different formulas and I'll show you some examples on how to use those. Keep these formulas close to you so that you can reflect back to them and decide which one you need to use for each question. The first question we're going to work on here is a ball is spun in a horizontal circle 60 centimeters in radius at the rate of 1 revolution every 3 seconds. What is the ball's velocity and what is its centripetal acceleration? So the first thing we're going to figure out is what formulas relate to velocity and the centripetal acceleration. Right here at the top of the screen you can see I have both the velocity and the centripetal acceleration. There is more than one option, so I have to decide what do I know. The 60 centimeters, that's my radius or my r. At a rate of 1 revolution, that tells me how many times I'm going around. So this actually is my theta, because I've gone a complete circle. Every 3 seconds, that's my time. So I have r, theta, and t. So I'm going to look at my velocity formulas. Looks like with r, theta, and t, I should be using this one. So I'm going to go ahead and write down that formula. V equals theta times r divided by t. Now before I do that, I'm going to go ahead and go over here and decide what I want. Centripetal acceleration, I can do the velocity squared over r, or I can do theta squared times r over t squared. I could use either one of those in this case. I know all of these same values here on the second one. That's exactly the same as I've got for this velocity. I'm also going to find the velocity, so I could just take that answer, square it, and divide it by the radius. Doesn't really matter, so I'm going to go the first one. So the acceleration, I'm going to do v squared over r. You could do the other one and we should end up in the same position if you wanted to. So now we're going to plug in the numbers so we can see what we get. V equals my theta. I'm going to do this in radians. 1 revolution is 2 pi. I should be working in radians because degrees don't work the same. Times my radius, which is 60, divided by my time, which is in 3 seconds. My 60 is in centimeters. My 3 is in seconds, so my answer is going to be in centimeters per second. 2 pi times 60 divided by 3. I could do some of this in my head. 3 goes into 60 twice, 2 times 20, so I get 40 pi centimeters per second. That would be the exact answer. If you wanted to go ahead and do 40 times pi on your calculator, I haven't done that, so I'll take just a moment to do that. So it's approximately 126 centimeters per second. Okay? So now what we're going to do is what is its acceleration? So it's increasing. So I'm going to come over here. I've already found v. I'm not going to use the 126. I'm going to use the exact answer of 40 pi. So 40 pi, I'm going to square that. I'm going to then put it over r, which is our radius, which is 60. This 40 pi squared, it is centimeters per second squared. So if we think about our units, we're taking centimeters per second and we're squaring both of those. Then we're dividing by r, which is our radius, which is our seconds, which, oops, I should have wrote seconds there, not 60. I already know it's 60. And it's actually our radius. So this cm is going to take away one of these cm's, so our answer is going to be in centimeters per second squared. So I'm going to take that initial answer, I'm going to divide it by 60. Oh, I forgot to square it. I was wondering why it wasn't working out. So I'm going to square it, divide it by 60, and I get approximately 263 centimeters per second squared. So here's my velocity, here's my acceleration. If Knoxville, Tennessee is at a latitude of 36 degrees north and a longitude of 83 degrees 55 minutes west, and Denver, Colorado is at a latitude of 39 degrees 44 minutes north and a latitude of 104 degrees 59 minutes west, The radius of the Earth is 3,960 miles. How far is it from Knoxville to Denver? So since we live on a planet that is circular, we can't just do a flat line velocity or a linear velocity. We have to do an angular. And actually, since we're looking for a distance, we're not actually talking about how fast something is going. We are going to do the formula that deals with angular distance. So if you want to go ahead and look at the formulas at the top, here is our angular distance. So we're going to be going through that whole formula. Now your L's are your latitudes and your M's are your longitude. All that matters is you keep them the same. So notice if you start here with L1, I have to have M1 first. If I mix those two up, I have to make sure I mix up the two at the end. So I'm going to go ahead and just plug in what I know. So I'm looking for the distance. My pen working again. Cosine of D, D is what I'm looking for, is sine of the first latitude, 36 degrees, times sine of the second latitude, 39 degrees 44 minutes. Now I'm going to add the cosine of the first one, first latitude, times the cosine of the second latitude, 39 degrees 44 minutes. Now I'm going to multiply again by cosine, but this time I'm using my longitudes and I'm going to subtract them. 83 degrees 55 minutes minus 104 degrees 59 minutes. Again, because I started with 36, I have to start with 83 degrees 55 minutes on my longitude. So I'm going to go ahead and plug all this in, and I did already head and do that for the sake of the time. When I plug that in, I get, still have the cosine of D on the left, and that is approximately 0.9563. Because I'm looking for D, I'm actually going to do the inverse cosine of 0.9563, and when I do that, I get D is approximately 17 degrees, or if you wanted your answer in radians, 0.30 radians. Now, that tells us that angular distance between them, so that is the degree measure like in the arc length. So I'm going to show a little picture here. So remember when we were doing arc length of a circle, and this 17 degrees or whatever, or the 0.3, that is this right here. This is D. And I'm actually being asked to find from here to here, so I don't get to stop with that. I have to go one more step. So I have to go back to my arc length formula, which is where knowing it in radians is helpful. My arc length formula that I had written down was S is R theta. My radius is 3,960. My angle in radians is this 0.30. So I'm going to go ahead and multiply those together. If I go a little bit farther out than the 0.30, just so I can be more exact, I get an answer of approximately 1,174.93 miles. So that's how far apart Knoxville, Tennessee is from Denver, Colorado. Now obviously that would be as what we call the crow flies, not as roads go. Okay, next one. A steel cylinder 8 centimeters in diameter is to be machined in a lathe. Oops, we went too far. If the desired linear velocity of the cylinder surface is to be 80.5 centimeters per second, at how many RPMs should it rotate? They are asking, let's see, how many RPMs, revolutions per minute. So we're going to have to do some dimensional analysis. I'm not sure if you did that in any previous math classes. That is one of the things we consider to be a pre-skill to what we have here. The 8 centimeters is the diameter. So I have a diameter of 8 centimeters. I have a radius of 4 centimeters. I have a linear velocity of 80.5, so that's my V, 80.5 centimeters per second. And I'm going to figure out how many revolutions per minute. Okay, so First thing we're going to do, because we're trying to get to revolutions per minute, is we're going to switch and look at what this is. So I need to know the angular velocity. Angular velocity, it says is, if I look at my formula, it's my velocity over my radius. So my velocity is 80.5 over my radius of 4. Okay, so I'm going to get 20.125. Let's look at the units. My angular velocity of 80.5, that was in centimeters per second. The 4 was in centimeters. You can see how the centimeters cancel. The 20.125 ends up being in radians per second. So I'm getting there. I'm in radians per second, and they want me to be in revolutions per minute. So when I work with dimensional analysis, I set up a little table. So I'm at 20.125 radians per second. And I have to convert until I get to revolutions per minute. So I need to think, okay, what do I know about revolutions and radians? I know 1 revolution or full circle is 2 pi radians. So I'm going to put 2 pi radians and 1 revolution. Now how did I know where to put what? I put radians on the bottom because I need this radian to cancel with the radian on top, because if something is on top and bottom, they cancel out. This puts me in revolutions, but I'm currently in revolutions per second. So now I have to change my time. If I'm in seconds and I need to get to minutes, I have to think, what do I know about seconds and minutes? Well, there are 60 seconds in 1 minute. So my seconds here will cancel with my seconds here. Notice the only thing I've left is revolutions and minutes, and they want me in revolutions per minute. So I'm where I need to be. So now I have to do the math. So I'm going to take 20.125 times 1 times 60, and I'll go ahead and do that on my calculator so you can do it with me. My top number ends up being 1207.5. And the bottom I have 1 times 2 pi times 1, so that's 2 pi. So I'm going to take my 1207.5, divide it by 2 pi, and I end up at, I have revolutions per minute of approximately 192 revolutions per minute. So in 1 minute it's going around approximately 192 times. Okay, so on this one here, revolutions per minute, we're talking about things moving in circles, and it also reminds you of that because it's a cylinder, right, which is a circle. So look for those terms that help us know that we're doing angular. Okay, the last one we're going to work with, an engine requires 6 seconds to go from its idling speed of 600 RPMs to 1500 RPMs. What is its angular acceleration? Okay, according to those formulas up above, our angular acceleration formula is alpha equals the angular velocity at the final minus the original angular velocity divided by time. Okay, well, let's see, what do I know? I know time. I know time is 6 seconds. I don't know WF or WO though, because those numbers that are given to us are in revolutions per minute, and angular velocity is not in that, it's in some form of radians per time. So I'm going to have to do a little bit of converting. So the first thing I'm going to work with is the WF and the WO. So let's go ahead and just start with the original angular velocity. So let's see what I know. In the original, it started at 600 revolutions per minute. My goal is to get to radians, and since my time is in seconds, I need to get to seconds. If that would have been in minutes here, I could have stayed in minutes, but it's in seconds. So I'm going to go from revolutions per minute to radians per second. So we're working kind of backwards from the problem we did in the last one. So what do I know? I know that 1 revolution is 2 pi radians. So that way my revolutions cancel and I'm in radians. I'm halfway there. Got to go with my minutes and seconds. I know that 1 minute is 60 seconds. So my minutes cancels and I'm in radians per second, which is angular. So 60 times 2 pi is 120 pi over 60. 120 over 60 is 2 pi radians per second. And I'm just going to go ahead and leave it there. It's not going to hurt anything. Okay, so now I've got to do the same thing for the WF so I can use them in my formulas. So my final angular velocity, right, is going at 1500 revolutions per minute. I'm going to do the same ones. So I've got 2 pi radians over 1 revolution. That way my revolutions cancel. I have 1 minute over 60 seconds. That way my minutes cancel. So I'm going to do 1500. Oh, I just realized this is 600, not that. So this should be 100. That should be 1200. So that should be 20 pi. That's going to be a big deal if I miss that. Okay, so the top down here is 1500 times 2. That's 3000 pi. The bottom is 1 times 1 times 60. So 300 divided by 6, that's 50 pi radians per second. Okay, we're almost there. So what I do have is I have my original angular velocity, I have my final angular velocity, and I know my time is 6 seconds. So now I can actually find my angular acceleration. So my angular acceleration sorry, I'm not sure why it's doing that. Let's see if we can get it to quit. Is the WF, which is the 50. Okay, I gotta figure out why this is doing this. I do not want it doing that. Okay, so it's the 50 pi, no, it's not even writing, minus the original, which is 20 pi, divided by the time, which is 6 seconds. 50 minus 20 is 30, so I have 30 pi over 6. 30 goes into 6, 5, so it's 5 pi. Just to make this be a number that actually makes more sense to us, 5 times pi is approximately 15.7 radians per second squared. And it's seconds squared because the top numbers are in seconds, the bottom numbers in seconds, so I actually have seconds squared. So it's going 15.7 radians per second squared. And that is my angular acceleration. As you're going through this section, make sure you use the formula sheet so you know which formulas are used when, and if you have any troubles, let me know. That is the completion of Chapter 5.